Victoria Station was built in 1844, during the height of the Industrial Revolution. The station, this Grade II listed building, and the Liverpool to Manchester Railway it initially housed was all engineered by George Stephenson, the man today considered the father of British railways. The station's rich history remains visible today, with this facade completed in 1909, Victorian exterior canopies of glass stones still shining, and even a war memorial dedicated to the soldiers who left Europe from Victoria Station during the First World War.
The old roof underwent demolition during 2013, during which time a temporary scaffolding structure was constructed to allow the station to remain in use during the renovation process. After the old roof had been removed, the next stage was to install the new roof and mezzanine walkway. The new roof was designed to span an area of 8,500 meters squared and is composed of 15 steel ribs of different lengths, which support 410 ETFE panels to make up the entire structure.
Perhaps one of the most striking features of this station building is this parabolic arch. The parabolic arch is upheld by 15 steel ribs and supported by cantilever beams along the station concourse. However, as you'll notice, on the other side of the station, no such columns are needed. This is because the force of the roof is translated down through the curve of the arc and into these huge concrete buttresses on the corner, allowing trains to pass freely in and out with no columns needed.
Now, the roof structure of this station is in the shape of a torus, which is the mathematical shape of what a bagel is. So it just goes all the way around, but since it's not a complete circle, it's only half of a bagel.
It's then cut into 1/4, and this section of the bagel represents the section of the tunnel that we are looking at. As you can see, we have used this black line to represent the tram line that goes through the tunnel.
This column, placed to uphold the station roof, has a circumference of 2.09 meters and an estimated height of 20 meters. We can use Euler's buckling formula to find the maximum compressive load this column can withstand before it buckles. The formula is defined as pi squared multiplied by the second moment area and by Young's modulus of steel over the effective length of a column squared. We know that Young's modulus of steel is equal to 200 times 10 to the power of 9 pascals. We can estimate the length of the column to be 20 meters, and we know that the constant giving the effective length of the column is 0.7, since the column is fixed at the floor at one end and pinned to the roof beam at the other. The second moment of area is a property of the cross-sectional area, which reflects how the mass is distributed with respect to the centroidal axis, and hence influences the chance of buckling. Its general formula is given by the integral of y squared with respect to the area. We know that Young's modulus of steel is equal to 200 times 10 to the power of 9 pascals. We can estimate the length of the column to be 20 meters, and we know that the constant giving the effective length of the column is 0.7, since the column is fixed at the floor at one end and pinned to the roof beam at the other. The second moment of area is a property of the cross-sectional area, which reflects how the mass is distributed with respect to the centroidal axis, and hence influences the chance of buckling. Its general formula is given by the integral of y squared with respect to the area. We know from structural research and from hearing the beam echo when we tapped it that the beams are hollow and hence have a ring-shaped cross-sectional area. The second moment of area for a ring shape is defined as pi over 2 multiplied by r1 to the power of 4 minus r2 to the power of 4. As you can see from these pictures, we have used photos from the station to idealise the supports and the beams. We have assumed that the roof is uniformly distributed, as this makes our calculations easier. You can see that there is a pin joint here and a fixed support at the wall. For the purpose of our calculations, we have assumed the beam to be straight, and since its weight is 80,000 kilograms and its length is 96 meters, we can calculate that the uniformly distributed load is 64.2 kilonewtons per meter. Here you can see the calculations that have been done in order to calculate the support reactions at these points. On this page you can see the shear force diagram and the bending moment diagram for this idealized section of the beam. You can see that there is a decreasing gradient for the shear force diagram, which results in a parabolic curve in the bending moment diagram. As you can see from this diagram, we have taken equilibrium of moments about point B, taking into account the forces that are acting on this structure at the different points due to the weight of the beams. In these pictures you can see circled the truss that we have chosen to idealise for our calculations. It is located near the main entrance of the station, so is very important in the structural stability. Here you can see the idealisation of this triangular support. We have assumed a uniformly distributed load on top here to simulate the weight of the roof, and on the right hand side a triangular load for the effective wind loading that this structure would experience since it is exposed to the outside. This is a triangular load since the wind pressure will increase as the height increases. The ETFE roof has an approximate weight distribution of 3.4 kilograms per meter squared. We will therefore use this value as the UDL applied. To find the force applied, we simply need its weight, i.e. 3.4 times 9.81, which gives us a value of 33.35 newtons per meter. These reaction forces are due to there being a pin joint at this end of the truss. Since it is pinned, there must be two reaction forces, and since it does not allow any movement other than rotation, there will be no bending moment force at this joint.